Are there any questions? Okay, well, that was easy. Why don't we just do the quiz and get it done? We last left off, just wrapped up chapter 3. We're about to start with forces. And the definition of a force, stated at the very end. How do you know if a force is acting on you?
Pushing pull.
There we go. That's probably the best working definition. Phones away, please. All right, so let's just start out with, it's a push or pull. There's a formal definition that it's an influence that might cause acceleration, which to me is so incredibly vague to be worthless. And so I'm just going to start out with a checklist here of the forces that we will use for the first month or two. All right, so FTONG, or Fort Ong, F stands for friction. The symbol I use for friction is what I sort of call a Baroque F, just sort of a curled F. T stands for tension. And the symbol I use for tension is a capital F with a subscript T. And the reason I don't use capital T for tension, and if you look at some of the old test answers, that it's possible I use capital T, but at some point we're going to end up in a situation where we need capital T to stand for something else. And so it's easier, in my opinion, to start out not using capital T for tension when we do our force diagrams and use F sub T, then later on go, all right, so now it stands for something different. O stands for other. And the symbol is problem dependent. N stands for normal. The symbol I use for normal force is a capital Y. Primarily, the physics textbook I used in high school used a capital Y for normal force, and it sort of stuck. Yes?
Wait, is this chapter 4?
Yes.
Okay.
And we don't use capital Y for anything else. If you want to use your own symbol, please don't use capital N in our diagrams to represent normal force, because newtons is the unit of force. And if you use capital N for normal force, then that would be a valid expression, and there's enough confusing symbols. So in 152, there is a situation where the unit and the symbol are the same. We don't need to add to that. G stands for gravitational force. And there are two symbols here for gravitational force, depending upon the situation. There is W, if we're talking about weight. And then there's F sub G, if we want the general, F sub G, the generalized gravitational formula, generalized gravitational force. And we'll be hitting the generalized gravitational force, I think, in chapter 6.
F of G. That's what that is?
Yeah, that's a G.
Okay.
Capital F, subscript G. Some textbooks just go ahead and use capital F, subscript F for friction, and then capital F, subscript N for normal, and so on.
And now what's the first word? Oh,
That?
wait, no, is it for F of G? Something gravitational force,
Here, oh, generalized.
generalized.
So this is just here for the checklist. These are the symbols that would actually be used in a problem. So let's start out with the simple one, weight. What are the requirements? So this is checklist, name, symbol, what's that, Fox symbol, just, because these are the ones I'm using. Requirements, world. So weight is a force that is involved if you have a small object near a large object. So we need a small mass, with small in quotation marks, near, also in quotation marks, a large mass. A large mass in this situation is a planet or a moon or star. An elephant would be considered a small mass. The generalized gravitational force just requires two masses. Normal force requires contact between two objects. Tension, the requirement is a tight or taut rope, chain, string, whatever you happen to be using for pulling. Friction requires contact between, what's the shorthand for between? Is it V/T? Somebody that doesn't look right.
I use BTN.
V dot what?
I use BTN.
BTN? We'll go with that. That's no abbreviation. Contact between two objects and desired relative motion. We'll get into why desired and why relative are both in there. It doesn't require actual motion. Now, each of these forces will come in pair. Oh, other, I left out there. The requirement for other is a force of an unknown source or irrelevant source. And I needed a valve. And what I mean by that, this is, other typically shows up in a word problem. Textbooks usually have an other involved. A 3 Newton force is pushing on a box. Well, what's causing the 3 Newton force? I don't know, doesn't matter. All I know is there's a 3 Newton force. That is an example of other.
What does tension say?
Tension, a taut rope, chain, or string, whatever happens. And I think on one textbook problem, an arm. All right, there are not a lot of times that we can use always in this course, and so this is one of the few always. Forces. Always come in pairs. Each force in that pair acts on a different object, and in opposite directions. Now, if you want to be incredibly picky about this, we could go with forces come in pairs 99.9999999% of the time. But that obscure exception is graduate level physics. And that's if you go into probably a general relativity thing. Yep.
Well, could it be like three forces acting on each other? Because then it wouldn't be pairs. Or is that what you're talking about?
No, there would be only two. It'd be a pair. They're not three in it.
What if there's like one object and there's three ropes attached to it and all three of them get pulled at the exact same time?
That would be three different pairs.
Okay.
Okay, so since they come in pairs, the question would be, when I draw the forces on a diagram, in other words, when I do an analysis of an object and try to figure out what forces are acting on it, what are the directions of those forces relative to each other? So direction of forces with respect to each other. Friction will always be side by side pointing in opposite directions. Well, they're always going to be in opposite directions because they're part of the pair, then it will be in opposite directions. Tension, the pair of forces will point towards each other. Normal force will always point away from each other. Gravitational force will always point towards each other. And the other doesn't really matter. You're going to draw a force in the direction that the problem states, and you really only draw one of that pair. As in 3 Newton force is pushing on a box, I would draw the 3 Newton force pushing on the box in whatever direction is stated. I would not draw the other part of that pair, which is acting on whatever is causing that 3 Newton force. And then direction of forces with respect to objects. Because a force requires that there be two objects involved. So friction is always going to be parallel to surfaces of contact. I push on the table. The friction force acting on the table from the carpet, well, the surfaces of contact are horizontal, so friction is going to be acting horizontally. More specifically, on the table, it'll be acting this way. On the rock carpet, it'll be acting that way. Tension is always along the line of the taut rope chain, whatever it happens to be. I realize I'm just throwing stuff at you right now. We're going to apply it in just a moment. Other problem dependent. All right, normal. What does normal mean? It's a math term.
I feel like it'd be like a set variable. I'm thinking like in the previous problems of Earth and Earth 2. Those are like set variables.
Well, the gravitational acceleration is not set, definitely. But no, that's not what the math definition of normal is. All right, normal means perpendicular. And it's called the normal force because it's perpendicular to the surfaces of contact. Perpendicular to surfaces of contact. So the normal force and the friction force will be perpendicular to each other. And the gravitational force is towards the center of mass of other object. So there's gravitational force between me and the Earth. The Earth is pulling down on me, I'm pulling up on the Earth. Now, we don't notice the force I apply to the Earth because the Earth is so massive, it's not influenced as much as I am by it. The gravitational force on me from the Earth is acting towards the center of the Earth, center of mass of the Earth, which we assume is the center. And the gravitational force I exert on the Earth is pointing towards my center of mass, which is somewhere around here. Okay. Questions? Yes, Alan.
What's the last description for weight? Perpendicular to what?
Oh, that's for normal force.
Normal.
I got off track there.
Yep.
Perpendicular to surfaces of contact.
Okay.
All right, and since the excitement of what do we do with this? Any other questions before we actually apply it?
Gonna doubt that now.
All right, so let's start in the wonderful world of force diagrams. And the first force diagram we are going to do is box falling. Yep. We're going to take everyday things and we are going to beat it like a dead horse. All right, so the first thing I do is I'm going to draw a picture of what's happening here. So I have the ground and I have a box that is falling. And we're ignoring air resistance, but I'm going to put those there to indicate the downward motion. All right, so first thing, draw the diagram, or draw the picture. Next step, I have two objects here. I have the box and I have the ground. I'm going to draw them separately so I have a place to draw my arrows. Now on this one, they're already separated, but I'm going to do this just out of process. So I'm going to draw my ground. I'm going to draw the box. And this is where I'm going to do my work. So the first thing I need to do is figure out which forces are involved. So let me write down F tone. Are there any of these forces that definitely are not involved?
Friction.
Okay, friction's gone.
Tension. Yeah.
Tension's gone.
We can't say O for sure, correct?
Did I mention any additional force acting in this? Any hand of God, et cetera, et cetera? I just said it's a box fall.
So my question is, does it have to explicitly say that there is an extra force for there to be?
Pretty much.
Okay. So, it's common too.
Yeah. Others gone. So all we're left with is just the gravitational force. I'm assuming that this is a box of normal size and the planet is huge. So the weight is what we're involved in. So which way is weight acting on the box?
larger object is pulling the smaller object?
Okay, so which way am I drawing the weight on the box?
Down.
Yeah. So I draw an arrow downwards, put a little W there, to indicate weight. This is what I mean by using those symbols. Forces come in pairs, so where's the other force in that pair?
On the ground.
Acting up. So the planet pulls down on the box with weight, and so I draw my arrow down on the box with a weight. The box is pulling up on the Earth, so I draw my arrow up on the Earth. All right. Force, we're done. First force diagram. Okay, so rookie mistakes. Rookie mistake number 1. Flipping source and target. You draw the arrow on the target. The Earth is pulling down on the box. So the gravitational force from the Earth is pulling down on the box. So rookie mistake number 1, backwards. So I have seen way too many times the implication that the Earth is causing this box to go shooting up into the air. So a little Mr. Young sticker next to that. Rookie mistake number 2. No man's land. That's probably should be 2 different words, but no man's land. I've seen this way too many times, and I'm looking at that going, I have no idea what the intent of that person is. Which force is acting on which object? Now, I did go into no man's land, but I definitely have this touching the box, and that is definitely touching the Earth, and they aren't touching each other. I've also seen the overzealous like that, which is also